Hello everyone. Today we are going to uh, discuss this theorem, so which we stated earlier in the previous lecture. So this is about the notion of subgroup of a group G. Okay. So earlier we saw the notion of subgroup. We have seen its definition, and so where we have seen that uh, it is defined by a certain bunch of conditions, and this theorem, theorem 52, it allows us to determine whether a given subset, more precisely, whether a given non-empty subset of a group G, whether a non-empty subset H of a group G is a subgroup or not. It provides us a criterion to verify. Okay, it provides us an equivalent criterion, that is a simple, necessary, and sufficient criterion. By simple, I mean here that it is relatively easy to work it out, at least in several instances. Okay, so let's try to go through the proof. I might have discussed a bit about this proof in the previous lecture. I think you have also seen a bit of it in the video. So, but this content was not there in the PDF. Okay, yeah. So there are kind of two parts to prove, namely the if part and the only if part. So we are first assuming this condition, and then we are trying to show that H is a subgroup of G. So let's assume that for any AB inside H, AB inverse lies inside H, we need to show that H is a subgroup of G. Okay, so that's what we need to show. So let's first fix the notation that E denotes the identity element of G. This is a standard notation. Okay, since H is non-empty, one can pick an element from that. Okay, so let's call it H, denoted by H. And now we know that H and H inverse, we know that H and H, they are elements of H, right? So now if we apply this criterion, we get H inverse, which is this element. So this has to be an element of H by this hypothesis. Okay, in other words, we have established that E is an element of H using this hypothesis. Okay, now then we also note that H contains the inverse of any element of H. Why is that so? So you pick an element B from H, and then you know that E lies inside H, something that you have just established, and then you have picked an element B from H. So you have E and then you have B. So E times B inverse, which is nothing but B inverse, that has to be an element of H. In other words, there are two things that we have proved. We first show that H contains identity using the information that H is non-empty and this hypothesis, of course. Then using the same hypothesis, we show that H contains the inverse of any element of H. Okay, now we pick two elements from H, and then we know by this observation that H2 inverse has to lie inside H, right? And then we have H1, H2 inverse, right? So H1 is an element of H, H2 inverse is also an element of H, and now by the same hypothesis, we know that H1 and the inverse of this element, which is H2 inverse, and that has to lie within H. And one can show that the inverse of an element is that same element. So the inverse of H2 is same as H2. Okay, so you have proved that H1, H2 lies inside H, right? And then the second condition for a subset to be a subgroup is that it has to contain the identity element. That is something that we have already established, right? And the third condition is that it has to contain the inverse of every element of of H. That is again something that we have established. So we have established that H is a subgroup of G. Okay, so this completes the proof of the if part, and to prove the only if part, we need to assume that H is a subgroup of G, and we need to conclude this. This is straightforward. This follows from the properties of a subgroup, or the defining properties of a subgroup of a group. Okay, so if we pick two elements A and B from H, then you certainly know that B inverse has to lie inside H being a subgroup. Okay, and then you know that A is an element of H, B inverse is an element of H, so their product, it also has to lie inside H. So AB inverse lies inside H. This is something that we have proved from the hypothesis that I mean we are given two elements A and B of H. So you are done, right? So this is an important tool that we will be using very often. Okay, this theorem is a very important tool. Just one point to keep in mind, that we have to first verify whether the given subset is non-empty or not. If it is empty, then of course, I mean this part is vacuously okay. I mean then this is not of any use. Okay, then the point is that this part is vacuously true, but this part is false. Okay. Anyway, uh, yeah. So here is an interesting exercise. So this is somewhat. Just give me a moment. Hmm. Yeah, so in the previous exercise, what did we do? We took multiple. Okay, this is not similar to what we have been doing, or maybe similar. Okay, I leave it to you as an exercise. In fact, you can do something here. So, the question that I was wondering about is that whether there is a relationship between exercise 53 and example 49. So, you think about it, okay? So, I can try to write things down right now, but that won't be good. Anyway, so that I mean, you get an opportunity to work it out. So you start with an abelian group G, okay? Then we collect the kth powers of all the elements of G, okay? So what we get is denoted by HK. Rather, the set that we get by collecting the kth powers of the elements of G, what we get is denoted by HK. So this exercise asks us to show that HK is a subgroup of G, whatever that K might be. So K is a positive integer. One can also take K to be negative. You can even uh, uh, ask this question: is there any relationship between HK and H minus K? So yeah, I mean, is there any relation between these two? So you can think about this, okay? And there is another part which says that for any two positive integers K and L, if K divides L, then HL has to be a subgroup of HK, okay? Anyway, great. So, to show that HK is a subgroup, right? Okay. So we are going to apply the theorem that we learned just now. Okay. So it says that one way to show that HK is non-empty, we pick two elements xy from HK and show that xy inverse is again a kth power. This is easy to do because if x is g1 power k and y is g2 power k, then xy inverse is equal to this quantity, and this can be one can show that this is equal to this. So this is left as an exercise for you to see why does this equality hold. Okay, so there is something that one has to use. Okay, I'll leave it to you. So you may say that this is not a proof, this is a partial proof. Yeah, I agree with that statement. There is something that I have left. There is something that I have left for you, so please think about it. Okay, so I'm doing the rest, which is also quite easy. Yeah, so xy inverse is again kth power of some element, right? So we are done, but well, maybe not. What we have done is that we have picked two elements xy from hk, any two arbitrary elements. We have proved that xy inverse lies inside hk, and then by theorem 52, we cannot say that H is a subgroup of G unless we verify that H is a non-empty subset of G. Okay, so that is something easy to see. Since G is non-empty, there is an element inside G, you take its kth power, so HK has to be non-empty. So this is quite elementary, but this is something that one has to observe first and one has to indicate, okay? One has to point out, okay? Great. So hence it follows that HK is a subgroup of G, so by theorem 52, okay? Now you have another example, something that we have already seen, at least in some form, okay? Not exactly maybe this one, but anyway. So one can show that this set consisting of the points whose coordinates are, consisting of points inside R2 whose coordinates are from the set, okay, I haven't written, okay, whose coordinates are from the set 1, minus 1, right? So we can define a composition law there, which is component-wise multiplication. Then one can show that this forms a group. I said that this is a note, but maybe I should try to rephrase it. So it's an exercise for you to prove that this is a group, okay, under the prescribed composition law, okay. And then, okay, so again, let me try to edit a bit. So prove that the subgroups of this group that we have met just here, they are precisely all this, okay. So this is not too difficult, but this is a good exercise to make ourselves comfortable and familiar with the notion of a subgroup. Okay. So by the subgroups I mean that these are all the subgroups. Okay. Oh, okay. So I have added this precisely. Note that the subgroups of this group above are precisely this. Okay. Uh, Great. Then then there is an interesting exercise, so which is similar to the previous one, example 54 in the spirit. Now it doesn't say that note that, it rather says that you have to prove. So this is no more an example, this is an exercise right now. I can also turn this into an exercise maybe. Great. So here one has to show that if you collect the points of R3 whose coordinates lie inside this set 1 comma minus 1, then then that set forms a group. That is what you have to prove, that this set forms a group under the composition law, which is coordinate wise multiplication. That is, if you take 2 points from G, then you multiply them coordinate wise. Okay, there are several things to verify that whether whether this is well defined or not, that is whether star is a map from G cross G to G, and then there are again, like, this is very similar, right? Yeah, this is very similar to what you have already seen. For instance, you have seen, actually you have done several exercises. For example, S1 with respect to the composition law that was prescribed probably in the first or the second lecture. So we have done how to establish that some such subset, some such set is a some such kind of easy set to set which is easy to deal with, whether that is a group or not. So now here is an interesting exercise which is which is similar in the which has the same spirit as that of the exercise above. So there one has to determine the subgroups of G comma star. Okay, here is an exercise for you to show that U2R is a subgroup of GL2R. Okay, so we have got GL2R is this, and U2R is the collection of all these matrices of this form. Then you see that U2R is a subset of so this is subset of the above one. Okay, so yeah, that's the first criterion to be a subgroup. First one has to have a subset, right? And then once you have this subset you see that this identity element lies inside U2R because you can take X to be 0. So what you have seen is that U2R is a non-empty subset of GL2R. Okay, and then if you pick 2 elements, we are going to show that the first element times the inverse of the second is an element of U2R. Okay, so if you do this computation, then you will see that this is equal to 1 and then X minus Y 0 1. So this is certainly an element of U2R by definition of U2R, and then it follows that U2R is a subgroup of GL2R. This follows by theorem 52, and so is the previous one. Okay, great. Okay, so here is an interesting result that we will only state but we will not prove. So this is known as division algorithm. So this is something we are familiar with in some form or the other, which says that given two integers a and b, okay, where b is positive, then there exists something called quotients and remainder. Okay, they are unique. Let me read the statement. It says that, okay, very naively speaking, if you would like to divide an integer a by a positive integer b, then you get a quotient and then you get a remainder, right? And remainder has this property and quotient has to be an integer. You know that, we are familiar, from our prior experience, we know, or at least we believe, that this quotient and remainder has to be unique, and that's what this theorem says. Okay, you may wonder, why do you call it a theorem? This is a bit difficult to explain because mathematics is done in axiomatic approach. So you first try to write down certain bunch of condition that you would like your underlying set, in this case that is a set of integers, that you would like your underlying set to satisfy, and then based on those bunch of hypotheses, okay, you try to deduce the properties that you are probably familiar in a natural way. Okay, so for example, the high school geometry that we used to do, namely the Euclidean geometry, it is based on, I think, 5 axioms. Okay, so based on those five axioms, so you can deduce several results. For instance, that how do you call the medians of a triangle, they are concurrent. So this is something that we know from our usual experience. People have been drawing medians and I mean for years at least. This is probably at least 2000 years old result, or maybe 2300 years old result, I don't remember. I mean that this Euclidean geometry, right? Yeah, but I mean, yeah, this Euclidean geometry and the in particular the statement that the medians of a triangle, they are concurrent, right? Mm, mm, I think they're called concurrent, right? I mean, they meet in a single point. I forgot they're called concurrent or coincident. I forgot. I'm sorry. Okay. Anyway, so this is a theorem because it follows from a bunch of axioms, and namely the well ordering principle of the set of positive integers. So one uses that to prove this result. Okay. So here this states that if you have two integers a and b where b is positive, then there exists unique integers q and r such that a is bq plus qr, okay, where r has this property. Okay, we are going to use this division algorithm, okay, to prove an interesting result. So earlier we have already seen an exercise. So okay, here actually you have collected the multiples of n, but for some reason I have changed the notation a bit. So here we will be collecting the multiples of k. So k times z. So k times all the elements of z. Okay. So k times z. I mean k and z next to it. This notation is defined to be the subset of z, which we know to be a subgroup of z. Okay. Here z is equipped with addition. Okay. Yeah. So this subset is a subgroup of z. This is something that you have already seen. I think you have already seen, right? We did prove that this is a subgroup, right? Yeah, so this is a subgroup of z. But maybe you can also try to apply theorem 52 to see that this is a subgroup of z. The verification will be just one line or maybe two sentences, something like that. First, you have to verify that this is non-empty. I mean, you have to observe rather. Okay, so this is quite easy, but this is something that we need to indicate, we need to observe in order to be able to apply theorem 52. Okay, because theorem 52 has a hypothesis that H is a non-empty subset of G, right? Anyway, so you already know that this is a subgroup of G, I mean subgroup of Z, this KZ. Then the main statement, the principal statement of this theorem 58 is that every subgroup of Z is of the form KZ for some integer k. K could be 0, it could be 1, 2, 3, 4, or minus 1, minus 2, minus 2, minus 4. Okay, for you can also try to think about what is the relation between minus KZ and KZ. Okay, an interesting question to think about. I think you see the answer immediately. Okay, so now we try to get into the proof. So we pick a subgroup of Z. We certainly know that 0 has to lie inside H. Okay, and if H contains no other element, in other words, it contains no non-zero elements, then H is equal to 0, and that is same as 0Z, right? Okay, so we have proved this result that that the subgroup H, we have proved the result for this subgroup H, that this given subgroup H here is of this form K times Z under the hypothesis that H contains no non-zero element. Okay, so otherwise, if H contains some non-zero integer, otherwise when H contains some non-zero integer, then we are going to argue that H has to be of the form Kz. We'll use division algorithm in that argument. Okay, so we pick, since H contains the inverse of any of its element, so there are positive integers, right? Because if you pick some non-zero integer from H, that is either positive, that is either negative, or either positive or negative. So if that is positive, then of course you see that H contains some positive integer. If that is negative, H being a subgroup has to contain its inverse, right? So the inverse of a negative integer is positive. So H has to contain some positive integer. Okay, so we pick the smallest positive integer lying inside H. Okay, so we pick the smallest positive integer lying inside H. So here, there is something that we are using here, but I don't want to state it. Okay, of course you see it immediately, I suppose, that H, that K, that inside H there has to be, if there are positive integers, then one can certainly, quote unquote certainly, one can pick up the smallest positive integer, right? So let's denote it by K. And now you know that H is a subgroup of Z. Okay, so H contains any positive multiple of K, right? And Since H is a subgroup of Z, you use the fact once again to show that H contains the inverse of the positive multiples of K. Okay, so and then the inverse of the positive multiples of K are the negative multiples of K, right? The negative ones. So H contains the positive and negative multiples of K. In other words, H contains Kz. H also contains K times 0, right? Okay, so H contains Kz. Now we are going to apply the result that we have learned a while ago, just a statement, to show that H is equal to Kz. So it suffices to show that H is contained inside Kz. Okay, there is any element of H is a multiple of K, right? So you pick an element A from H, and then you apply the division algorithm, okay, to the integers A and the integer K, okay. So then you will get a quotient and a remainder. So they're unique, but you're not going to use that information. You're going to get integers Q and R, where R has got this property, and A is equal to KQ plus R, okay. Since H contains Kz and H also contains the integer A, H has to contain A plus K times minus Q, right? And which is equal to R. So the integer R lies inside H, right? On the other hand, note that the integer R satisfies this inequality, okay? Whereas K is the smallest positive integer lying inside H, okay? So in that case, these inequalities imply that R has to be equal to 0. There is no other option. And once you have proved that R equal to 0, you have established that A is equal to K times Q, right? That is, no matter what element we pick from H, it is a multiple of K, okay? And that proves that H equal to Kz, okay? So let me conclude this lecture here. There is something interesting that we are going to start in the next lecture. And there will be a series of discussions on the upcoming notion that we'll be learning in the upcoming lecture. So let's just put it for the upcoming lectures, okay? Okay, so let me conclude here.